Let's start in the beginning with the two guys who got this intermodal thing going in the 1950s. It was Malcolm McLean and engineer Keith Tantlinger working together that transformed how freight was moved, which led to the expansion of global trade as we know it today. The 2011 New York Times obituary for Keith summed up his contribution as one that helped bring about the vast web of international trade that is a fact of 21st century life. More than any other innovation, the modern shipping container is now acknowledged to have been the spark that touched off globalization. What America and the world needs now is another spark of innovation to eliminate the costly and time-consuming congestion at our ports and on our highways. I don't know where this is, but the condition is global. Global trade, mainly from Asia, has clogged American ports with intermodal containers and was a major problem during the pandemic, especially the San Pedro ports at Long Beach and Los Angeles. So bad, even 60 Minutes reported on it. As consumers, we all eventually pay for this inefficiency. Congestion was also bad at the Savannah port. In fact, a pop-up port at the Statesboro, Georgia airport, 50 miles away, was used to relieve congestion. An average of 25% of containers leave American ports by rail. It needs to be 100% for destinations more than 200 miles. Here's a video snippet from that 60-minute segment.
It used to take 2 days to get cargo off the docks. Now it takes 9. To see why, we took to the air.
Look at how packed this is here. Yeah, totally packed.
We flew over the sprawling ports of Los Angeles and Long Beach. 40% of all U.S. imports come through here. We saw stacks of marooned containers, dormant cranes, loaded rail cars sitting idle, the country's busiest ports packed to the gill, and out at sea, more than 80 ships stretched to the distance, a new record. They used to pull right in. Now they can wait weeks.
It wasn't that long ago, during the pandemic, that intermodal containers was a hot topic. We still have the problem. It's just not as bad today. However, the inefficiency, high cost of moving these containers at the ports, and heavy reliance on trucks to transport containers is still with us. Productivity improvements that would reduce labor costs or speed things up continues to meet with strong union resistance. So, American ports are the most inefficient in the world and resistant to change, especially anything to do with automation. And interstate congestion in rural areas is occurring more and more often. In this case, there's been 2 accidents, one in each direction. Check out the number of big trucks that are part of this traffic jam. It's obvious that trucking should not be America's logistics backbone. You might ask, since rail is 4 times more efficient in the use of fuel, why not use rail? It's a simple answer. Processing costs at terminals are too high, and then you have high drayage costs, sometimes $5 and $6 per mile, to transport the container from the rail terminal to the dock of the customer. And it takes at least twice as long to get a container in and out of a seaport terminal than it does a truck. This chart illustrates the ports at San Pedro Bay. We're still using the same equipment as we did 50 years ago, so it's no wonder that things haven't improved. So not only are American ports slow, but so are American rail terminals, since they use the same equipment and processes. And it's not cheap moving containers at $150 per lift. Every container has to be stacked to await placement on the truck or rail vehicle that will move them out of the terminal and on to where they need to go. Whatever it is that stops the movement of a container in a port is a constraint in the port process. And Dr. Goldratt states that every process has a constraint that stands in the way of achieving a goal. He also says that focusing on the constraint is the fastest and most effective way to improve profitability. Stacking containers in queues is clearly a non-value-added step, a step that is costly and introduces a major time delay and is a constraint and bottleneck. According to Peter Drucker, This step should be removed, not automated or made more efficient, as many foreign ports and a few in America are doing. Automating the stacking process will not solve the problem. The stacking of containers in queues is the kind of activity that is identified as a time trap when lean principles are applied to this process. It occurs because of deficiencies in transportation capabilities involving either the process or equipment or both. Containers are stacked primarily because the transport vehicle, either truck or rail vehicle, is not immediately available when the container is lifted from the ship, and if it were, the container would be placed on the vehicle, and the vehicle would leave the port and transport the container to its destination. A much bigger problem exists on American highways and involves the drayage transport of containers and also the dry freight being transported in 53-foot trailers that could potentially be transported by rail. To do that, the high cost and slowness of intermodal terminals must be eliminated as a constraint. This presentation presents a concept of operation that removes the constraints and provides a solution approach to both requirements. So this is our goal. Develop the next generation of intermodal rail. We're calling it Intermodal 2.0. The goal is to develop a container transportation capability that's much faster and cheaper than trucks at distances greater than 200 miles. This would be a short-haul intermodal rail capability that would truly be transformational. This is a chart that shows an estimate of the break-even point today. Intermodal rail doesn't begin to start being used until at least 550 miles. It's not competitive with trucks on highways, and this is what it needs to look like. The Intermodal 2.0 capability should work similar to an Amazon warehouse, but better. Lots of technology and things moving synchronously. Think of it like a synchronous container transportation machine with all the parts oiled, moving with no friction, perfect timing and humming. No queues, no container stacks, containers always moving toward their destination. This is our first estimate of key performance parameters and should give everyone an idea of what the economic impact might be for America and throughout the world. So, it's short-haul intermodal rail at 200 miles, reducing terminal costs by 50%, limiting container dwell times at many intermodal terminals to 12 hours, increasing agricultural exports 100%, and reducing big truck 53-foot van traffic on our interstate highway system by 50%. This is the performance level that will make Intermodal 2.0 systems America's logistics backbone. These are the 7 key Legos of the Intermodal 2.0 capability. The most technically challenging is the low-cost, robotic gantry crane. Many small gantry cranes will be used in each terminal to quickly load and unload containers. A double-stacked container train set of 35 well cars will be moved by a double-ended set of 4-axle, hybrid battery catenary locomotives. A catenary will be constructed along sections of the railway to recharge batteries en route. AI-based logistics software will control the flow of containers. System operations and movement of train sets will be interfaced to legacy systems and positive train control as required. This is what a 35 double-stacked well car train set looks like. The total length with 2 locomotives would be roughly 2,000 feet and weigh approximately 2,400 tons. Today's large, centralized intermodal container transfer facilities will be augmented by hundreds of mini intermodal terminals that will function as highly networked, decentralized facilities, very similar to the way our internet does today in routing packets of data. The key system attributes of the mini intermodal terminals include small footprint terminals, synchronous operation, and no on-site storage of containers or chassis. The terminal design is essentially an industrial siding with many robotic gantry cranes, lifting containers for pickup by trucks that will transport them to and from customer docks in the local area, which would most likely be within a 10 or 20-mile radius. This includes a micro-terminal that may be used by short-line railroads when the main line is available. This is the robotic gantry crane that's the key and secret sauce to this new capability. And it's a disruptive innovation, if there ever was one. It's smaller, slower, electric, rail-mounted, and autonomous, which dramatically reduces operating costs. Standardization and manufacturing scale will make this critical Lego affordable for everyone. And that includes developing countries, which is super important. This is the preliminary set of key performance indicators of the mini intermodal terminal that the system engineering and Lego development team must meet. As can be seen, this is fundamentally a design-to-cost project, and that's what makes this project so challenging and difficult. By the way, Georgia Tech and Auburn engineers love projects like this. This is where it gets more interesting. A key feature of this capability is that it will enable the use of electric trucks for drayage, since distance required by drayage is greatly reduced to local areas, which is well within the range of all Class 8 electric trucks. Also, it should be affordable for every small town in America. So, rather than have a few high-performance, high-cost gantry cranes, lifting many containers, we have many lifting few, and we do the job to be done a whole lot faster and cheaper. The goal of the Macon Port Express demo project is to demonstrate that key performance parameters have been met and economic metrics for revenue and operating costs meet our requirements and can be replicated at other ports. The demonstration will involve building terminals, constructing a sectional catenary, and validating the concept of operation using the new battery electric locomotives and robotic gantry cranes. The demo project involves a stackless transfer of containers from ships directly to a mini intermodal terminal at the port, where it is loaded on a shuttle train for a 164-mile trip to a mini intermodal terminal near Macon, Georgia. Electric drayage trucks will then transport containers to destinations in Middle Georgia and the Atlanta metro area, all within 24 hours of discharge from the ship. This is the Garden City Terminal at Savannah with ship-to-shore cranes and hundreds of container stacks and about 250 rubber-tired gantry cranes that cost $2 to $3 million each. Hundreds of drayage trucks enter and leave the terminal at multiple gates, transporting 75% of containers that leave or enter the terminal. Containers from around the world enter the Savannah port, and many are destined for Chicago, St. Louis, and Memphis. It is estimated that more than 1,000 containers go to Atlanta every weekday by truck. The demonstration uses the existing Georgia Central Railway between Macon and Savannah, owned by the Genesee and Wyoming Corporation. Norfolk Southern owns an alternate line between the Savannah port and Macon. The two end-point mini-terminals will be a few miles south of Macon at an industrial park in Franklinton. Shown on this slide and the other, at the Garden City Terminal at the Port of Savannah, two micro-terminals will also be constructed and demonstrated near the Georgia towns of Dublin and Vidalia. The red lines on the green routing illustrate the locations of the electrical catenary required to recharge the battery electric locomotives. The shuttle train will travel at a max speed of 25 miles per hour over a combined catenary length of 40.7 miles. The idea is to locate the catenary for recharging the locomotive's batteries at locations where construction and maintenance costs are lowest. One last and most important topic to be discussed is the initial estimate of operating economics and business case. So, assuming 2 round trips per day and 70 containers each way, 365 days per year, and charging $3 per container per mile generates an annual revenue of $50 million with an annual electric bill of approximately $101,000 at 6 cents per kilowatt hour. The electricity cost for the trip for each container is $1.98, assuming constant speed of 25 miles per hour and perfect environmental conditions. At 55 miles per hour, the cost would be $4.93. Let's take a quick look at the greatest impact this system might have, starting with America's Class 1 railroads and the idea of moving short, 2,000-foot-long shuttle trains. This is a diagram showing the typical geographic and spatial layout of intermodal container transfer facilities. Notice the distance between the terminals, which can easily be 300 miles or more. This is where the intermodal action occurs between rail cars and trucks. Trucks are used to move containers to and from rail terminals and warehouse docks. The new approach will put terminals, represented by the green circles, at closer spacings. This will dramatically reduce the high drayage costs, since the average drayage distance could potentially be reduced 80% or more. This is a first look at where intermodal transfer could potentially be located in South Georgia. Moving containers by fast, low-cost rail could really give an economic boost to rural America. South Georgia would be a great place to validate this concept, as both CSX and Norfolk Southern are operating there, as well as many short-line railroads. The concept of operation involves replicating this function into an orthogonal system of corridors. This is illustrated by the green lines of 4 east-west corridors and 8 north-south corridors. The intersection of the corridors would be a transfer point where containers would be set out for pickup by a shuttle train traveling in a correct orthogonal direction that would take it to the final destination terminal. Only one, set out, would be required for any destination. For example, a container that originates in Savannah with a destination of Chicago would be picked up by a northbound intermodal shuttle train in Macon, Georgia, which is cell 3, and require one transfer at cell number 14. It would be picked up in an average time of 12 hours by a westbound shuttle that drops the container at cell 22, which is Chicago. The red irregular-shaped objects represent geographic service areas that Class 1 regional or short-line railroads provide intermodal services to, which is depicted in this graphic. This illustration shows how the Savannah container moves from Savannah to Macon by a movement within the cell. This slide illustrates the synchronous timing and dwell of the container drops and picks at the terminal and the 30-minute time constraint for getting this done. Only one shuttle train can be in the terminal, so speeds of all other shuttle trains will be controlled and timed to avoid conflict. The key point is that terminal dwell time is a function of the number of robotic gantry cranes a terminal has. Some terminals may only need one, and a few terminals may need as many as 16. This capability does not exist and will not exist until several critical items or Legos are developed. Intermodal 2.0 uses legacy track and increases system capacity without interfering with existing rail traffic. It's competitive with long-haul trucking, and it's a green project that generates carbon credits for new rail traffic, including credits for green drayage. The potential for taking market share from trucks on highways is high, as well as generating revenue from new customer segments not currently served, as Dr. Christensen described. The goal is to bend the cost curve to the point where short-haul intermodal rail of 200 miles becomes a reality. The benefits of the Intermodal 2.0 capability will be an increase in the use of intermodal rail services throughout America, and that includes rural America. Thousands of new, fast, low-cost container transfer terminals at small and medium-sized towns will dramatically decrease the use of trucks to move containers from large, slow, centralized terminals to and from small towns hundreds of miles away. This will reduce transportation time and cost, highway congestion, and greenhouse gas emissions, and will provide an economic boost to rural America by increasing exports of agricultural products like alfalfa hay or cotton and other products that are manufactured for domestic or global use. Doing this will generate significant revenue from carbon credits and improve investment returns and make many intermodal capabilities in smaller towns economically viable. One last point, which is the icing on the cake. This has to do with the annual revenue generated from carbon credits, which is estimated to be $2.4 million for the Macon Port Express, and this does not count the carbon credits generated from the electric drayage trucks used to deliver containers from and to the Macon terminal. And get this, for the National Shuttle Train Network, it would be $570 million. That's all for now. Thanks for watching.